Thank you. Yeah, I can hear myself. Great. Not too great. I'll see if I can make that less distracting for myself. So happy to see so many here. We'll see who's the most excited. I'm super excited giving this talk, and I'll try and stay calm, not get overly excited. So I'm going to talk about making computers do things, and hopefully at the end of the talk you will understand what I mean by that. Just a short kind of preamble, just to give a kind of what I will actually be talking about. I will talk about what is a computer, just so we kind of understand what I mean by when I say making computers do things. And then I'll give some examples of making computers do things throughout sort of what I've done as a researcher. And then I'll look a little bit into the future, how we might in the future make computers do things. Okay? So what is a computer? When I was an undergraduate student at Chalmers around 2002, 2003 maybe, one of the lecturers were asking us in the room, could you tell us what a computer is? What does it look like? Please go up to the whiteboard and draw a computer, right? And so almost everyone drew something like this. Not as artistic as this, because not everyone is as good as ChatGPT at drawing computers. But everyone basically drew like a screen and a box and a keyboard and a mouse, because this is what a computer was to most people. This is what a computer looked like, right? But the reason why he asked us to do it, well, this was in a course on ubiquitous computing, which was about, in the future, computers will be sort of, ingrained around us. It will be everywhere. And today we sort of have much more things and a bit much kind of richer conceptualization, I think, of what a computer is, because these computers are in everything, right? It's embedded everywhere. We have computers in our watches, computers in our phones, obviously, smart speakers, even our cars are now computers on wheels, right? So computers takes many different shapes and forms. But when I think about computers, I think about things that are more something like this, much more a kind of abstract notion of what a computer is. So here we have some sort of central processing unit. That's sort of like something that can compute stuff. There's some memory to it. It can remember things. It can also be storage. And then there's some input device and some output device. And for the person from computer science, this is a von Neumann architecture. And really what the von Neumann architecture kind of was the first thing that enabled software. So software is when we kind of write instructions to the computer that we then load into the computer, and it can do new things. Before software, if we wanted a computer to do new things, we had to basically rewire them, like a switchboard operator, a telephone operator having to unplug a cable and putting it somewhere else, right? You had to change the hardware to make the computer do new things. But with this architecture, all of a sudden, we could write software. And that's sort of how we make computers do things, right? But let's take a step back, maybe a step forward from von Neumann, but step back from today. So the first time that I saw a computer, this is what I saw. So I was like 5 or 6, and there was like this blue thing, this blue rectangle on a TV screen. I didn't understand anything, but I understood from the people in the room that this was something special, right? So my parents and my brother, they seemed excited about this blue thing, right? And what it was this. This was the Commodore 64. This is what it looked like. Some people might remember it. Can't really see it here, but hopefully on the next screen we'll see it. What was special about the Commodore 64 is that when you started it, it just had this screen. See if we can see it better if you do this. So it's basically just telling you something about the computer. This is a Commodore 64. There's some basic in it. But what's most important, it says ready. And what it's ready for is an instruction from the user, right? Like the computer is ready now. What do you want it to do, right? And we can start giving it instructions. So we can tell it, print Mattias. And it prints Mattias. I hope you can see this, right? And we can say it to do other things. We can write it to say hello or whatever, right? Perfect. And And we can also make programs, right? So we can tell it not just to do one thing, but do several things. So we can write a program by saying 10 print hello, and then 20 print Mattias. What I'm doing here is I'm kind of numbering the instructions. So they will be executed in the order that I give them. So 10 will be executed first, and then 20 will be executed second. So it will print hello Mattias, because it will first run the instruction on line 10, and then the instruction on line 20, right? And for those who have done this before, the first program that anyone who had a Commodore 64 did was this, right? And so what happening here is that the first line says print Mattias, we'll print hello in this case, and then line 20 says go back to line 10 and run it again and again and again and again. And I have no idea how to start this, and this is what you did back then. You turn the computer off and then turn it back on again, right? And it's ready. Now, to make it a little bit more interactive, you can, of course, do interesting things, such as read something from the input, ask the user for something, request some input. And then we can say, hello. I want to do this correct. And if we run this, it first waits for me to give some input. So I can write Mattias. Oops. And then it will say, hello, Mattias. Right? So it uses the input. So now it becomes a little more interesting, because before that, every time you ran the program will be the same thing. But now all of a sudden, it starts to react to the user's input. Right? And this is what programming is. This is how we make computers do things. And this is how we still make computers do things. So back to the ordinary programming. And this is great. So what I was doing, what you were using, the sort of instructions that it was waiting for, was something that expressed in BASIC, right? And BASIC is great, but BASIC is also very basic. It's great and really expressive to do the things that are basic. But as soon as you want to do more advanced things, things become a little bit more difficult. So some of the first kind of games that me and my friend were doing back then was like these text-based story games, right? They gave you a story. Hello, you're in the forest. If there's a tree in front of you and there's a stick on the ground, what you want to do? One, bash your head into the tree or pick up the stick. And depending on sort of what you answered, you could either die or you could finish the game. I think we never made a game where you could actually finish, but we always died. But if you wanted to do more advanced game, like the game on the right, BASIC just didn't cut it. Then you had to go a little bit deeper. You had to kind of basically tell the computer how to do that in a much more expressive way. So what I want to do now is I'm going to spend some time going through a couple of examples of making the computer do first buttons, then maps, steps, and screen time. Okay? That's what I want to do. And I'll do that by talking through some examples of what I've done. And for each of these examples, if you want to have an app for like 25, 30 minutes, what they all will come down to is that kind of things that are very easy to do now have not always been easy. Okay. So, but we have to make them do these things. That's kind of the point here, in order to do other stuff and to do my research, right? So this is an old example from work I did not very far away from here. An application called Push Music. And basically what it was a music listening and sharing application, where people who ran this on their mobile device, this mobile music player, music files could jump between these devices as you pass them, right? So you listen to your music, and then you walk past someone else who had this same player, this Push Music device, and songs themselves try to autonomously figure out, maybe I will be liked on that other person's device. So there were sort of these agents as music files that try to find the person who would want to listen to them, right? And we implemented it. I implemented this on PDAs. They were Wi-Fi enabled. I had a bunch of. They were quite advanced for the time. I had to implement like service discovery protocols. I had to implement ways of transferring these files between these things. A lot of advanced things. But that's not what I'm going to talk about. What I'm going to talk about is something we might just take for granted here, which is like, how do I do the buttons? But there's a bunch of stuff you can interact with. There are these thumbs up, thumbs down, a play button, skip, things like that. Even these things are buttons. And they just don't come for free, right? So what is a button? Well, we have the computer. What does it perceive? What is the input to this thing? And this was a touch interface or touch device. So it can perceive the taps on this like little screen, right? So you got the X and Y coordinate. That's it. You sort X, Y coordinate. And then for the output, it's just the pixels on the screen. So you can change the color of each pixel on the screen, but that's about it. So how do we make it into a button? Well, what is a button to the user? It's some sort of visual representation of a button that when you press it, something happens, right? You should be able to distinguish between pressing the button and not pressing the button, pressing outside the button. So I made a little emulator of a PDA screen. Like this. So this is an emulator, right? So we can see here, this is like my stylus, which is now the mouse cursor, mouse pointer, and we can see the coordinates. That's sort of what the computer sees. And then I've also implemented some stuff there, so that when I tap it, we can see where it taps. And that's actually the code that runs here. So this is the code inside. This is the computer sort of thing. This is not the instruction that the computer gets. And we have something that's called whenever it wants to draw something. And then we have something when some input is happening. So when someone taps the screen, some code is run. And this is the code that runs here. So just to figure out, how do we make first a visual representation of a button? Well, we can draw it, right? So now we have a button on the screen. Beautiful little button. At least it looks like a button. We can draw another button. Oops. Another button. Click me too. Oops. So we have two buttons, but they're not buttons, right? They just look like buttons. Just because there's something on the screen doesn't mean it's a button. We have to also write the code that the computer executes to understand that it's a button. And the way we do that is to have to compare a bunch of numbers. So X is the X coordinate and Y is the Y coordinate, X and Y. So the button is at X50. We need to make sure it's to the right of that. We need to make sure it's to the left of the end of the button, which is about, we can do this, we can give it a width. It's about 100, so 50 plus 100, or width, sorry. We need to make sure that the Y coordinate is greater than wherever the Y coordinate is, and less than the bottom of the button, which would then be 100 plus the height. We want something to run, height 30. And then we say print button pressed, just to make sure that it works, right? And hopefully this works. Hopefully I'm a good coder. So now we press outside the button, and then we press inside the button. It should say button pressed. Woohoo! We made a button, right? Because now it distinguishes from me pressing the button and not pressing the button. And so we can press this button. No, of course not, because that's not a button. We have not said that that's just a button. It just looks like a button. So to do that, we would need to write this code again and say that now the Y coordinate is 200. Let's just distinguish with. So now, hopefully, we can press it. Button press 2, right? So a button is just not a button just because we say it's a button. That's my point. We have to make the computer do buttons. Now, of course, we don't have to do that because, of course, everyone wants to have buttons on the screens. This is not something you don't have to write it all the time. But the computer is always doing that somewhere, right? Now you can just write on, if you write a web page, you make a button like this, just write the text, or if you're in some other programming framework, software framework, you can write things like that. It's easy, but still, the computer is always running that code. It's just made it easier. So that's how we make computers do buttons, okay? Let's look into something else. Let's see how to do maps. Maps are fun. So this is from a project called Columbus, where we figured out that there were a lot of photos that were starting getting geotagged. So a geotagged photo is a photo where it has some metadata about where it's taken, right? Today, every photo we take with our mobile phones, of course, has this location in them because the phone knows where it is. But it didn't always be the case. But they were starting to get larger and larger collections of these geotagged photos, and we wanted to create experiences where how can we tie this together? How can we make an experience where the photo and the location is taken in has to be kind of experienced together? So we wanted to create an application where, in order to see a photo from a particular location, you have to go to that location. So if I wanted to see a photo from Paris, I had to go to Paris. If I wanted to see a photo from the pier where the boat arrives here, then I have to go there and see it, right? And in order to do that, we wanted to create an application where you could see the map. You could have a map and you could see the photos on it. So quite trivial, quite simple, simple idea. But we had to show the map somehow, right? And the question is, what is a map? Let's go through that. So this is a map. It's basically a picture of Earth. I guess it could also have been a picture of Mars if it was a map of Mars, but let's stick to Earth for now. And so you would think that, okay, so if I want to see Gothenburg, you just zoom in on this map. But of course, if you have built the pictures before, you know that doesn't work. The pixels get too big. We don't want to see this image. We want to see something more like this. And the problem is that you would think that, okay, we'll just take the picture of this resolution and make the whole Earth like that. But the picture just becomes too large. We can't manage that in these computers, right? And just to kind of make that clear, we can figure out how many pixels is Earth, right? So this is a zoomed-in picture of Kuggen. I don't know if anyone saw that, the round building outside here. It's about 60 meters in diameter, and on this picture it's about 100 pixels. This is a picture of Earth, and it's 12 million meters in diameter. It's, of course, it's a three-dimensional. So we need to figure out how many kind of pixels is the surface of it, really. Or how many meters, square meters is it? So Kuggen is about 3,000 square meters in surface area, and Earth is about 510 trillion, something like that, right? Quadrillion, I don't remember. Anyway, so Earth is roughly 140 billions of Kuggen. So you can fit 140 billion Kuggen on Earth, right? And that's about 1.4 quadrillion pixels. A lot of pixels. It's about a petabyte, if each pixel is 1 byte, which is a little bit too much for these phones currently. Maybe not in the future, but currently it's a bit too big. So the way computers deal with this, or the way people who make computers do things deal with this, is they make several different versions of Earth by dividing it into tiles. If you just want to have like the picture of Earth, you just have it in one tile. Each tile has the same resolution, and the resolution 256 by 256, for instance, something like that. And then if you want to have like a more zoomed in version of that, you just make sure that you need more tiles for Earth or whatever region, right? So the more zoomed in you get, the more tiles you need to cover the same surface area. So if you want to make an app that can show these maps, right? What does the phone actually do? Or what does the computer in the phone actually have as input and output? Well, the input is sort of the location, latitude and longitude. Where are you on Earth? So if you want to see a particular area, you need to know where you are on Earth. And then as output, it's just the pixels on the screen again. And we need to figure out, as persons who try to make computers do things, need to figure out how do we put the right pixels on the screen, right? Fortunately, it's very simple. There is a formula which is the Mercator projection. They can take the longitude and latitude and turn it into an X and Y coordinate if you have like a map of the world. And so you write some code to figure out which tile you should pick from a large collection of tiles. And then you can just figure out how to draw them on the screen and tile them together and put them together. So that's a little bit more code. I'm not going to go through that code, but that's basically how you do it, right? And so we were doing this in around 2007, 2008. And, presto, we had maps on the phone. Great. We could do our research. We could look at what is the user experience of having that sort of capability. In 2008, September, Android was released. And about 6 months later, Android 1.5 was released in April. And when they released it, maps, they realized that people want to have maps, just like before. People want to have buttons on screens, right? And Google realized for Android, people want to create these location-based services. And so we want to have maps. So with that, they made it super, super simple to add maps. Now all you had to do was say, just like we said, oh, put a button here. You could say, put a map here. So a few years earlier, had to write a lot of code. Now you didn't have to write a lot of code. But at the same time, of course, in Google Maps, they're still running that same code or a similar type of code, right? There's nothing different. Let's go forward to another example. So in 2013, I went to Glasgow, University of Glasgow. We had 2 projects there. One project was called Football Fans in Training. And it was like an intervention. We did this with medical researchers. And it was supposed to be an intervention to get football fans. You can imagine football fans in Glasgow, not always super healthy. They like to drink beer, they like to watch people play football. And maybe they don't like to play football themselves as much. And so the health researchers were figuring this is a problem. Let's try and fix it. So they wanted to create an intervention where they could get them to be a little bit more physically active. And our part in that project was to kind of create technology around that. Could we put this sort of intervention into an app? So what did we do? Well, we tried to figure out what is it actually that kind of measures physical activity in day-to-day life. And typically that was the health researchers were using steps. And so we were thinking about how can we use steps also in the mobile phone. We did 2 different apps. One was just looking at what happens if you see your own number of steps and compared it to others. And another one where we tried to make this activity of counting steps more of a kind of collaborative activity, where we created a game. So people we divided people in teams. Each team had a ball. Only the person with the ball could score for the team. And essentially, if you had the ball, then your steps counted as the team score. Now, if you were then going to sit on the couch for a while, you might not want to have the ball if someone else in your team is about to be active. So you wanted to pass it. So we turned this whole thing into a kind of collaborative coordination activity of counting steps. But we had to figure out how to count steps. Now, at this time, activity trackers were becoming more and more common, more mundane. We also looked at how they were used. But they all had kind of one thing in common. That is that they were using something called accelerometer to figure out or trying to measure steps. Okay? Before that, or rather in like the 1500s, Leonardo da Vinci had devised the first mechanical step counter, and he actually counted steps, by having a bunch of levers and stuff and gears going around. Who knows what he did? But they were actually counting steps. These things are not really measuring steps, but they are measuring acceleration. So the computer in these things, and also the computers in the phone that we then implemented apps for, just has an input accelerometer data, and the output of that should be some sort of numbers that we can then show on the screen, perhaps. But what we want to have is a count of how many steps I've taken. So what is the accelerometer? It's basically something that looks like this. If you want to, you can scan this QR code, and you will get something fun. I'll show you in a bit what that is. I'll see if anyone is listening. But basically what the computer sees is just these squiggly lines, right? These squiggly lines is sort of what the accelerometer is over time. I mean, the computer doesn't really see the squiggly lines, you just see the numbers, right? But it's easier for us to understand those numbers as these squiggly lines. And if you have started this on your phones, then you have something looking like this. So this is what the computer sees, and this is essentially me walking around the kitchen last night, trying to see if I can see the steps, right? And so we need to figure out, in order to count steps from this data, we basically need to see if we can infer this and turn it into steps. So how do you do that? Well, there are many different ways of doing it. One way is to turn these 3 squiggly lines, because it's X, Y, Z coordinates. I'm not going to go into the details of that. Turn it into another kind of squiggly line. That looks like this, and it looks like here, as you can tell, there's like some noise here, and then something happens. Maybe that's where there are some steps taken. We can look at that and see, okay, so it looks like this. I know at this time I did take some steps, but what can I see from this? Well, maybe here are the steps, right? So maybe we identify, we say, okay, we think that this is where they took steps. And so maybe they took 4 steps. And what I have to do to make the computer count these steps is to figure out then how I can kind of infer that this is the steps that were taken. And there are many ways of doing that. There are many machine learning algorithms you can apply for it. And there are tons of papers you can read about people doing that. But they're all just trying to infer the steps from these squiggly lines. So it doesn't always get it very accurate. But that's what you have to do. But at the same time as we were doing this, I mean, activity trackers were a thing. People at Google and people at Apple realized that, wait a minute, we have accelerometers in these things. Why don't we just add steps to them? And so around 2014, 2015, these phones that we all have all been counting our steps using these sort of squiggly line analysis. And to get these steps now, we don't have to go through all that effort looking at squiggly lines. We just ask the device, give it a number of steps in the last hour or so. So for instance, when Sebastian were implementing work from home app, he didn't have to bother with accelerometers and squiggly lines. All he could say was, okay, just give me the steps and I'll present them in a nice way. And we can compare how much have we been walking before or less the pandemic, like we did in this app, work from home movement. Okay, final examples. We've done buttons, we've done steps, and we've done maps. So now let's look at screen time a little bit. So at the same time as I was in Glasgow, I did two things. I did the football fans in training, and the other thing I was doing was trying to figure out how can we figure out what people are doing on their smartphones, right? So this was 2013. Everyone was having a smartphone. We didn't know too much about what people were using them for. There was not really any data on that, although, and the reason for that was very hard to get. It might seem like a very trivial thing to figure out. Just, well, why don't we just look at it and log it and store the data that people are using their phones for? But it was not. When I came there were about 2 or 3 researchers who've been working on that for a while, trying to figure this out. And I joined, and I was there for 4 years, and we tried to figure it out. And I think we did manage to figure it out. But there was like 3 or 4 very senior kind of mobile app developers trying to figure this out. And why is that? Well, let's take a look at it. How can we infer what people are doing on their mobile phones? The input is essentially like all computers keep a log of what's happening inside of them. And that's good for developers to figure out what's wrong with it when something goes wrong. Like a car mechanic goes into the car and sees like what has happened in the car, why is it not starting, or why is it acting up? The computers are doing much the same thing. And it might look something like this, or we might imagine it looking something like this. I made this manually. This is my own log, right? Someone wakes up very late in the morning and starts their phone, 7:25, having a sleep in, right? So they start the phone, and then they keep it on and doing nothing with it for a while, and then Messenger is launched at 7:26, okay? And then they maybe read the messages, do whatever, and then the phone goes to sleep 43 seconds later, okay? And then maybe they have some breakfast, have a shower, whatever, and then the phone wakes up again. So again, we're just seeing what the computer sees, right? The phone wakes up, and a few seconds later, the home screen is open. So they press some button and go to the home screen. And then from the home screen, Chrome is launched, right? And then they're reading the news maybe for a couple of minutes, and then the phone goes to sleep, okay? Easy peasy. How hard can it be to infer kind of screen time or what you do with the phone from this? I mean, it's super simple. We can see the phone starts at some time, and then the phone goes to sleep. Great, the phone is awake then. You count that as, how much you've been using your phone. And then the phone wakes up again, and then the phone goes to sleep. So that's obviously the time that the phone is awake. We could do it much more granularly by looking at, how much are you using Messenger, how much are you using Chrome. The Messenger thing gets a little bit more complicated because when the phone goes to sleep, we need to remember which app they were on so that when it wakes up again, they're still on Messenger, right? Even if they're only doing that for a few seconds to find the home screen. But still, you should count that probably, right? Super simple. But I said we worked on this for a while. Why is this not like this? And just thinking of this problem is sort of giving me PTSD. Because this is what it looks like in reality. This is what these logs look like, right? And you might be thinking, but it's so simple. You just have to clean it, just filter out those events that you want and then analyze them. If only it was that easy. If only we didn't think of that, right? It's not that easy because things are coming out of order. These things are not as deterministic as we might think. For one, they have several processors now. It's not one computer, it's several computers. Things get out of turn. What happens if your Wi-Fi goes out or if the memory is broken? There's so many different things that just act up. It's never as simple as that. So to do this, to go through this whole thing, it's obviously, according to me, very laborious. But not anymore, you would think. So in 2018, Google and Android realized, or Google and Apple realized that, people seem to be concerned about the time they spend on their devices. Maybe we tell them how much time they're spending on their devices. They will keep using their devices because obviously they want people to use their devices. So we'll just give them this data for them, screen time. So Apple has screen time, and on Android is something called digital well-being. You can see how much time you're spending on your device and what you're doing, right? So now we obviously don't need to go through all these logs. We could try and get it from here. I wish it was as simple as that. It's not as simple as that. We're currently working on a project where we're trying to see how much time you're spending on your device when you're asleep, or when you should be asleep, or around your sleep time. And we are still sort of trying to get the funds to implement that. But we're sort of there. It's much easier now than it was 2013, 2014. So those were the sort of 4 examples. We have shown how we can make the computer do maps and steps and screen time and the 4th one. Buttons, thank you. The most trivial one. So there is this researcher called Alan Kay. He was sort of, he's a big figure. He's one of the people who were part of the team that sort of made the computers look the way they look now. He did the kind of part of the team that did, Windows icons, menus, pointers, that we have a screen with those buttons on them. There are windows, there are icons and stuff like that. And he had this saying, famous saying, the best way to predict the future is to invent it. Now, I wouldn't be too bold to say that I've been inventing the future, but I've been trying to kind of look into the future, kind of creating these alternative futures, right? And try to figure out what they might look like. What can the computer really do? And if the computer can do that, what would the world look like if the computer did that, right? That's sort of what I've been trying to do. The research I've been following is like a what-if question. What if this existed? What if the world was a world where this thing was a thing? What would it be like to live in that world? And I've been doing that essentially by making computers do things. And as we've seen, as we've been trying to show that making computers do things gets less difficult over time, right? After a while, we just assume computers should be doing something, and then someone else has made the computers do that very simply, and we just leverage that. The problem is we're always trying to try and make the computers do new things all the time. So even though the first thing we try to do is easy, now the next thing we want to do is not as trivial, and now we wanted to make even other things. But the computer can really do anything, right? We just need to make them do so. So I've been sort of talking about this past, present, or past future, and I now want to talk about the present future, if you will. Like, where are we going from here? How do we make computers do things? And first, let's think a little bit more about how it is in our everyday lives we maybe make computers do things. Right? So this is a user, this guy here. He has a task, and in order to accomplish this little task, he needs an app. And he needs a new app. The app doesn't really exist yet. He knows there should be an app, and he wants to do it. So how do we do that? Well, he finds this guy. Let's call him Sebastian. He's a developer. Now, he's really good at kind of making computers do things. He's really good at kind of making instructions, and he do that by writing code, much like the print Mattias go to 10 kind of code, a little bit more advanced. And by doing that, eventually, after a while, he gets an app from that, right? So he writes the code, writes the instruction for the computer then understands what it should do, and we have an app, an application. And so we install this application on some sort of device, and now the user has a device through the interface for which he can use the app. And he can accomplish his task. Easy peasy. So I think that's sort of how it looks now, right? That's one way of looking at how these things work. We have a user who talks to a developer who writes some code. The code turns into an app that we then can run on a device. And we've all been sort of using ChatGPT. I don't have to explain ChatGPT. Some people are using it all the time. Some people are skeptical, probably. But everyone has heard about it, right? And ChatGPT came out in 2022, and it was enabled sort of by these large language models, as they're called. But they wasn't invented with ChatGPT. Already in 2021, GitHub, which is kind of this large software repository company, now owned by Microsoft, they had a product called Copilot, which also used a large language model. Because as it turns out, these large language models are not just very good at to chat with and ask questions and do all kinds of things you shouldn't be doing, but they're really, really good at writing code. Really, really good at writing instructions for the computer, making the computer do things, right? And they're also very good at understanding what we want them to do. So since 2021, a lot of people have been using that to kind of help you in writing code. They've been called coding assistants. And over time, these sort of coding assistants have become better and better so that we don't actually have to write any code ourselves at all, or less and less of it at least. So now we just tell the Copilot in this case to write some code for us that does something, and it just does that. And it's much, much faster writing this code. It doesn't have to go in and say, print Mattias and go to 10 and all of that and turn the computer off and turn it back on again. It probably does that, but it does it so fast we can't see it, right? But so we don't really need to kind of attend to the code there. At the same time, there are now a lot of companies and products coming out. They're basically saying, you don't have to care about the code at all. You barely need to know anything about code. Just tell us what you want, tell us what the app should be doing, and we'll write the code for you that just does that. Okay? So you shouldn't care about the code. Just tell the computer, tell me what you want, tell the AI what you want, and it happens, right? So the code just becomes sort of obsolete. We just get this app. We have an AI, tell you what you want, we get an app. We see the app is not really exactly what we want, tell the AI to change it a little bit, and we get something new. Okay? So that's what we're starting to see now, which means that you don't really need to know how to write code. So sorry, Sebastian, but your developer credentials are over, just like us now. We just have ordinary people or users who have a task, and they can just tell the computer or the AI, write me the app. And after some time, we get it. But at the same time, we also have another sort of direction, which is we also have these agents, operators, whatever, AIs that can do the task for us. Not write an app, just do it for us. And what it does is that it can use the devices for us to do anything. It can browse the web or change our spreadsheets or do our research, write our papers, whatever. And it can just do it for us. So we just tell it, I have a task, and it will do it. Right? The AI will use the devices for us. So you can imagine then, okay, well, then we just tell an AI, we want an app so that we can do some stuff, and then we tell an AI to use the app to do it. Why would we need this app? Of course we don't. Of course we just tell the AI to just write the app it needs to write in order to do the thing it needs to do. Because surely it probably still needs the computer to do something. But the device here and the app is really not necessary for us to think about. We just need to think about there is an agent, maybe it uses a computer, right? Because this AI is kind of writing the instructions, making the computer do something, but those things just becomes obsolete. We don't really need to attend to those things anymore. We just have an agent that can do stuff, and then they can talk to a computer and tell the computer to do stuff. So essentially it looks like this. I have some task, we have an agent that does it. Boom. Excellent. And that's sort of what I'm interested in. I'm sort of interested in this future. What the heck is this? Right? What is a computer in this case? If I were to ask someone who lives in this future what a computer looks like, what would they draw? I don't know. Or even how it works. I mean, what is it like to live in a world where anyone can make computers do things? Like all of these things is sort of hinting to something new needs to be done. So this is the future. And this is what I want to look like. So I think the computer can do basically virtually anything, but we have sort of been restricted by what we have made the computer do. But if we can just tell the computer to do whatever we want it to do, and it can do it, what is it we are going to ask the computer to do? That's it. Thank you. Questions?